Our prior understanding of the universe's grand scale felt complete, but in the year 2004, the Hubble Space Telescope's Ultra Deep Field image presented a breathtaking panorama of approximately 10,000 galaxies, leading to estimations of 2 trillion across the entire cosmos. However, this groundbreaking observation was inherently constrained. It was merely a glimpse through visible light, obscuring much that lay concealed within cosmic dust and the spectral shift of distant light. Now, the James Webb Space Telescope has irrevocably expanded these horizons. In a remarkable observational endeavor lasting just 250 hours, Webb's Cosmos Webb Mosaic has unveiled not 10,000, but close to 780,000 galaxies, all captured within a celestial expanse no larger than 3 full moons, stretching back 13.5 billion years. The significance of this revelation extends beyond mere numerical increase. The fundamental principles governing cosmic evolution appear to have shifted. How could such intricate structures and advanced maturity emerge in what was previously perceived as an empty void? This is how the James Webb Space Telescope has fundamentally reshaped our perception of the universe's true immensity. In 2004, astronomers directed the Hubble telescope's focus onto a seemingly barren sector of the night sky in the constellation Fornax, allowing it to observe for over 11 days. The resultant image, christened the Hubble Ultra Deep Field, became a landmark achievement in modern astronomy. What appeared as an unremarkable expanse was found to harbor nearly 10,000 galaxies, each a vast constellation of stars, some emanating light from over 13 billion years in the past. This solitary image, a mere speck against the backdrop of the night, formed the basis for estimating that the observable universe contained as many as 2 trillion galaxies. For years, the ultra-deep field served as our most comprehensive chart of the distant cosmos, offering a window into the universe's nascent stages. Each point of light represented not a star, but an entire galaxy, each containing billions of its own celestial bodies. Nevertheless, Hubble's observational capabilities, however profound, were inherently limited. Its 2.4-meter mirror was primarily sensitive to visible and ultraviolet light. The most ancient galaxies, their light stretched and redshifted by the universe's expansion, had faded into the infrared spectrum, rendering them invisible to Hubble. Furthermore, obscuring clouds of cosmic dust lay between us and these remote celestial beacons, veiling entire populations of galaxies from our view. The Hubble Ultra Deep Field, despite its exquisite detail, was essentially a partial view, dictated by the limitations of its technology and the narrow band of the electromagnetic spectrum it could detect. It transpired that the universe held far more secrets than we had comprehended, awaiting a new generation of telescopes to illuminate what lay hidden beneath the dust and beyond the visible spectrum. The James Webb Space Telescope represents more than just a larger instrument. It is an observatory of a fundamentally different design. Its primary mirror spans 6.5 meters, far exceeding Hubble's 2.4-meter diameter, and collecting over 6 times the amount of light. However, its true revolutionary aspect lies in its observational range. Webb is specifically calibrated for infrared light, a spectrum that allows it to penetrate cosmic dust and capture the faint, redshifted light from the universe's earliest epochs, light that remained imperceptible to Hubble. Whereas Hubble's vision was akin to peering through a narrow aperture, Webb's perspective is akin to stepping back to admire an expansive mural. To grasp the magnitude of this advancement, envision the Hubble Ultra Deep Field as a photograph printed on a single sheet of paper. At the same observational depth, the Cosmos Webb image would unfurl to cover a mural 13 feet tall and 13 feet wide. The Cosmos Webb program leveraged Webb's unparalleled capabilities for an unprecedented survey. Over a period of 250 hours, it meticulously scanned a patch of sky approximately 3 times the apparent size of the full moon. Thousands of individual exposures were meticulously stitched together to create a single seamless mosaic, resulting in the most extensive and deepest panoramic map of the universe ever assembled. Within this singular field of view, astronomers have catalogued nearly 780,000 galaxies, each a vibrant metropolis of stars, some emanating light from less than 400 million years after the Big Bang. This is not simply an expanded perspective, it is an entirely new kind of celestial atlas. The map possesses sufficient depth to reveal the universe's most faint and ancient structures, and is expansive enough to capture the grand architecture of cosmic filaments, clusters, and vast empty regions. For the first time, astronomers can examine not just individual galaxies, but the comprehensive sweep of cosmic structure across billions of years, all within a single unbroken view. Webb's infrared vision and its extraordinary reach have provided a novel perspective on the universe, fundamentally altering our comprehension of both its immensity and its concealed intricacies within the vast expanse of the cosmos Webb mosaic. The nearer universe emerges into focus as a dynamic realm characterized by mature galaxies, intricate mergers, and colossal superstructures. Here, astronomers have identified galaxies in their prime, grand spiral formations, smooth elliptical shapes, and irregular forms captured in the midst of cosmic collisions. The scale of this map permits researchers to trace the aggregation of these galaxies into colossal filaments and clusters, which form the very framework of the cosmic web. Yet, amidst these familiar formations, one discovery stands out: a system designated as the Infinity Galaxy. This remarkable celestial object, catalogued at a redshift of 1.14, exhibits a distinctive figure-8 silhouette, representing two disk galaxies engaged in a near head-on collision. Each galaxy remains discernible as a compact red core encircled by rings of stars and gas, their orbital paths profoundly altered by the force of their cosmic encounter. The collision, estimated to have occurred approximately 50 million years ago, is not merely a spectacle of celestial violence. It has engendered conditions observed with unprecedented clarity. Between the centers of the two colliding galaxies lies an immense cloud of ionized hydrogen, glowing with the energy emanating from a hidden engine. Deep observations from both the James Webb Space Telescope and the Chandra X-ray Observatory have pinpointed the signature of a supermassive black hole, not situated within either galactic nucleus, but rather lodged within the intervening gas. Its velocity precisely matches that of the surrounding material, with a discrepancy of no more than 50 kilometers per second. This off-center black hole, possessing a mass approximately 1 million times that of our Sun, is accompanied by two additional black holes. Each of the original galaxies harbors its own active supermassive black hole, confirmed by their broad hydrogen emission lines. The arrangement is striking: three voracious black holes, all actively consuming matter, with only one residing outside a galactic core, nestled within the aftermath of the collision. The evidence strongly suggests a direct collapse origin for this unusual black hole, meaning it formed in situ from dense, shocked gas funneled by the merger, rather than being ejected or captured. Its presence, caught in the act by Webb's infrared vision, offers a rare glimpse into the potential mechanisms by which supermassive black holes might seed themselves amidst the chaotic process of galaxy formation. The Infinity Galaxy serves as a profound testament to the power of panoramic observation. Only by surveying such an extensive and deep field could astronomers detect such a fleeting and complex event. Its figure-8 morphology, with a black hole burgeoning in the void between, suggests that the universe's most powerful engines may sometimes ignite not within the hearts of galaxies, but in the turbulent spaces where celestial bodies collide. We now embark on a journey deeper into the cosmos Webb mosaic, traveling back to a period astronomers refer to as cosmic noon, an era approximately 10 billion years ago when the universe was at its zenith of star formation. The galaxies discovered in this epoch are not merely energetic. They are remarkably organized, exhibiting a maturity that challenges prior expectations. Webb's infrared vision is now revealing a startling paradox. Galaxies that have ceased their star-forming activities, known as quenched systems, appear in abundance during a period when they were theoretically expected to be ablaze with stellar birth. These dormant giants, some possessing masses comparable to the largest elliptical galaxies of today, lie quiescent amidst a cosmic landscape that theoretical models predicted would be dominated by young, chaotic systems. However, the surprises do not end there. Webb has also uncovered spiral galaxies with well-defined arms and stable, symmetrical disks, even at redshifts between 2 and 3. In cosmic terms, this represents a mere few billion years after the Big Bang. Conventional models posited that it would require significantly longer for the universe to develop such ordered structures. Yet, here, spiral arms gracefully curve around dense cores, and some galaxies already display central bars, clear indicators of settled, mature disks. The data conclusively demonstrate that disks capable of supporting these features were prevalent much earlier than previously anticipated. This early order is not merely an aesthetic phenomenon. The presence of stable disks and quenched giants at cosmic noon signifies that the processes responsible for suppressing star formation and shaping galactic structure must have operated with remarkable swiftness. The timeline for the development of cosmic complexity is rapidly contracting. Each galaxy observed from this era serves as a critical clue, compelling astronomers to reevaluate the speed and frequency with which the cosmos can transition from chaos to order. The map is not merely more detailed, it is actively rewriting the narrative of galactic evolution. At the very limits of Webb's observational reach, the record for the most distant confirmed galaxy now belongs to JD's GS Z14-0. Its light commenced its journey a mere 290 million years after the Big Bang. Not far behind, Mammoth Z14 sets a new benchmark at 280 million years. Both of these galaxies have undergone spectroscopic confirmation, their distances precisely determined by sharp Lyman breaks observed in Webb's NIRSpec data. However, the surprises extend even deeper. The Atacama Large Millimeter Submillimeter Array, ALMA, has detected oxygen emission in JD's GS Z14-0, indicating the presence of heavy elements at this incredibly early stage of the universe's existence, evidence that at least one generation of stars had already completed its life cycle and died. These galaxies radiate with the luminosity of hundreds of millions of suns, concentrated into incredibly compact and intense starburst regions. Their very existence, along with their chemical signatures, suggests that galaxy assembly and stellar evolution commenced at a pace that defies the standard cosmic timeline. Within the first 300 million years, the universe was already actively forging complexity. The discoveries continuously pouring in from Webb's new map are compelling astronomers to fundamentally rethink the narrative of the universe's formation. Galaxies and black holes are now known to have formed earlier and grown at accelerated rates, exceeding the predictions of existing models. Even the most distant confirmed galaxies, such as JD's GS Z14-0 and Mammoth Z14, are already radiating with heavy elements a mere 280 to 290 million years after the Big Bang. This implies that the cycles of star birth, death, and chemical enrichment had to commence almost immediately, compressing what was once believed to be a gradual billion-year process into an astonishing cosmic sprint. The established cosmic timeline, once perceived as a slow progression from simplicity to complexity, now appears more akin to a rapid-fire sequence of assembly and transformation. The pace of ionization, the growth of massive galactic halos, and the seeding of black holes all necessitate novel explanations. The earliest chapters of the universe's history are being rewritten, and the questions that remain will undoubtedly fuel astronomical research for years to come. In a mere 250 hours of observation, the James Webb Space Telescope's Cosmos Web Survey has charted nearly 780,000 galaxies, an astonishing increase of almost 80 times compared to the Hubble Ultra Deep Field's findings in the year 2004. This infrared panorama reveals structures and galaxies extending back 13.5 billion years, including record-breaking objects like Jadi's GS Z14-0 and Mammoth Z14, both observed less than 300 million years after the Big Bang. The data from the James Webb Space Telescope indicates that mature spiral galaxies, massive galactic mergers, and the presence of heavy elements appeared far earlier than current models had predicted. Nevertheless, crucial questions persist. How did galaxies and black holes achieve such rapid growth? What role did dark matter and feedback processes play in these phenomena? The timeline of cosmic evolution is being continually redefined with each new observation. It is important to remember that this map encompasses only a small fraction of the sky, serving as a potent reminder that our universe is even vaster and more intricate than we had previously imagined, with much yet to be discovered.